Moments of inertia, type 4, rolling discs and pulleys. B, rotating pulley and one particle. So it's not often these come up really, because obviously these are more seen in our pulleys and wedges questions. But this is a really, really nice question, so it's a lovely one to have a look at. Not all questions in applied maths are nasty, okay? So in 2004 we were given a smooth pulley, meaning no friction, and it has a mass of 3 kilograms and a radius of 0.3 m. So a lot of times our radius are given to us in terms of or. So here in this question we were actually told the radius is 0.3 m. We have one end of a light inextensible rope is attached to a point P on the rim of the wheel. So we can see P here if I just highlight it. So the string is attached to that point. And we have that it's inextensible, meaning it's not going to be bouncing up and down, so no simple harmonic motion either, okay? A particle of mass 0.2 kilograms then is attached to the other end of the rope, which hangs freely. And the axis of rotation of the wheel is horizontal and perpendicular to the wheel and passes through the centre of the wheel. The particle, we're told, is released from rest and it moves vertically downwards. So in other words, on release, we're going to find that the particle, 0.2 kilograms, will accelerate down. As it accelerates down, it's going to have a change in position. So its height above the ground is going to change by a particular amount. And it's going to accelerate down because of gravity acting on the block. So in other words, we'd have our mass, which is 0.2 times gravity. And of course we'd also have tension acting up away from it in the string, and we'd have some angular velocity as the disc is rotating, and then we'll also have linear velocity as the particle accelerates in a downward direction. So of course the first thing that we always do in these questions is, well, we work out what is our moment of inertia going to be, but it actually wants us in the first case here to find the kinetic energy gained by the wheel. So it's actually breaking the question down for us. So we're going to find the kinetic energy of the wheel first, given that the particle has acquired a speed of 1.2 meters per second. Okay, so to get our kinetic energy gained by the wheel, if we're looking at page 54 in our maths tables, we can see that our kinetic energy is going to be half I omega squared, because obviously the wheel is what we're looking at, and the wheel obviously is going to have angular velocity, so its kinetic energy will be a half I omega squared. So of course before we can work out the kinetic energy, we need our I, and we need to look at what is omega. So for the disc, we know on page 53 of our tables, so this is page 54 of our maths tables, and page 53 of our maths tables, then our disc is of course a half I omega squared, a half m or squared I should say, and my mass, we're told, is 3, and the radius is 0.3, and I have to square that, and that gives me my moment of inertia to be 0.135. Okay, and we also need to get omega. Now, we don't have our angular velocity, but what we do know is that we can look at the relationship between our velocity. So we know that V is equal to or omega, and therefore omega is going to be equal to V over or, and V is 1.2 and or is 0.3, and therefore that gives me an angular velocity of 4 rads per second. Okay, and that's of course page 51 in your tables. So now we have I and we have omega. We can now of course get our kinetic energy. So we say therefore the kinetic energy of the wheel is equal to a half times I times omega squared, and therefore our kinetic energy is 1.0, and of course our unit for energy is joules. So we had 5 marks for getting our moment of inertia. We had 5 for getting our kinetic energy formula, and substituting in and getting our kinetic energy was 1.08. So we had 15 marks, really handy 15 marks there, just for those 3 lovely little formulas. So the second part of the question says, when the particle has acquired a speed of 1.2 meters per second, find the distance descended by the particle. And again, we have to be careful here because it's correct to 2 decimal places. Okay, so of course, as it's descending down, we're going to have our principle of conservation of energy kicking in. So we're going to have a change in potential energy will be equal to the change in kinetic energy. So we'll have our mgh. So it's going to be losing potential energy and of course gaining in kinetic energy. Okay, and our kinetic energy formulas then are of course in our tables, and again that is page 54 and 55. And of course then you just need to know your conservation to put it all together. So what's our mass? Well, our mass is 0.2 times gravity times h. Okay, and we don't know what that distance that it's descending is. And we have a half times the mass, so 0.2 by the linear velocity, which we know is 1.2, and plus a half times the inertia, which is 1.35, times the angular, which is 4 squared. Okay, so simplifying all of that and rearranging to get h on its own gives us a value that it has descended a distance of 0.62 meters. Okay, so again we had 5 marks for our formula, and subbing in, and then 5 marks for the answer. So we had 30 marks in total for that question. 30. And really, really nice. Very handy 30 marks to collect that year, especially if you knew your proofs off by heart. It's a lovely little question, that.